So we've seen how we don't just have to have basis vectors that are our normal 1, 0 and 0, 1, the so-called natural basis. We can have different basis vectors that redefine how we move about space. In this video, we're going to define what we mean by a basis, by a vector space, and by the term linear independence, which is going to let us understand how many dimensions our vector space possesses. So first, let's define what we mean by a basis. A basis is a set of n vectors that are not linear combinations of each other, which means they're linearly independent of each other, and that span the space they describe. The space is then n-dimensional. This first criteria I can write down by saying that they're linearly independent if I can't write any of them down by taking some combination of the others. So for example, let's say I've got a vector b1 here. By taking multiples of b1, I can get anywhere along the 1D space of a line. If I take a second vector, b2, that isn't just a multiple of b1, then I can get anywhere in the plane of this board by taking combinations of b1 and b2, some number of b1s plus some number of b2s. And this is a 2D space. Now, let's take a third vector, b3. Now, for b3 to be a valid third basis vector, it has to be impossible for me to find some numbers, a1 and a2, such that I can satisfy this sum. So it has to be impossible for me to find b3 as some combination of b1s and b2s, where a1 and a2 are just numbers. That has to be impossible. And if it is impossible, b3 is a third basis vector, and b3 is linearly independent. If it is possible for me to find an a1 and a2 that satisfies that sum, b3 is then linearly dependent on b1 and b2, and it lies in the same plane as b1 and b2. And if it's impossible for me to find an a1 and a2, b3 must have some component out of the board, so I can then use b3 to give me a three-dimensional space. So that lets us define what we mean by the number of linearly independent basis vectors in our space. If I had a fourth basis vector, b4, that wasn't a linear combination of b1, b2, and b3, I'd have a four-dimensional space, and so on, up to as many dimensions as I like. Now, notice what my basis vectors b don't have to be. They don't have to be unit vectors, by which I mean vectors of length 1, and they don't have to be orthogonal, that is at 90 degrees to each other. But everything is going to be much easier if they are, so if at all possible, you want to use orthonormal basis vector sets, 90 degrees of unit length. Now, let's think about what happens when we map from one basis to another. The number line of the axis of the original grid then projects down onto the new grid and potentially has different values on that grid, but the projection keeps the grid being evenly spaced. Therefore, any mapping we do from one set of basis vectors from one coordinate system to another keeps the vector space being a regularly spaced grid, where our original vector rules of vector addition and multiplication by a scalar still work. It doesn't warp or fold space, which is what the linear bit in linear algebra means. Things might be stretched or rotated or inverted, but everything remains evenly spaced and linear combinations still work. Now, where the new basis vectors aren't orthogonal, then to do the change from one basis to another, we won't just be able to use the dot product. We'll need to use matrices instead, which we'll meet in the next module. So that's the formal definition of what we mean by a basis and by linear independence.